Hi everybody, welcome back to Chem 121. Hope everybody had a good weekend. Got some homework done and also maybe a little bit of relaxation in because you shouldn't work 100% of the time. I mean, I try not to. It doesn't always work though, so I definitely sympathize. If you spent all weekend doing practice problems, if so, good for you. Um, Midterms are next week, believe it or not. Um, the quarters I don't know if it feels like this for you guys, but being like stuck at home feels simultaneously like it goes so quickly, like holy crap, we're week 4? When did that happen? But also like, ugh, it's only Tuesday. So, like I don't know how to I have no semblance or concept of time. Um so what are we doing this week? Let's see. We're gonna finish chapter 3. We're gonna move on to chapter 4 and probably finish it too. And then next week we'll be on chapter 5. So after we finish chapter 3 today, there will be a quiz that goes up for chapter 3, and it'll be due next week. However, quiz number 2 for chapter 2 will be due on Wednesday, like we prescribed last week. So make sure to get that in by the deadline. Sometime on Tuesday, I will briefly mention the lab. And we'll talk a little bit about what you need to do for that. I am currently grading the first labs. I think for this class, I am finished with them because I sat down last night. I had time, and I was like, I'm going to grade as many as I can. Otherwise, I'm going to go crazy later on in the quarter. But I do have another class of labs to finish, and I don't like to upload the labs until all of my lab grading is done. So you'll get that back fairly soon, I suspect. Maybe not tonight, but definitely sometime this week. Things that I did notice on the lab were that a lot of people could do the calculations, so that's good. You could convert whatever to inches, or feet to inches, or so on and so forth. But the major issue for a lot of people was, of course, significant figures and how many should my answer have. And it was very apparent that a lot of people need to do more practice on that. So please make sure that you are brushing up on your sig figs and asking questions in the Discord if you have any. All right, we were on this slide. We answered all these questions last time we were here, so we were going to move on to isotopes. Let's talk about what isotopes are. I can have a certain number of protons in my atom, and that forces it to be a specific element. Because remember that the number of protons something has dictates its chemical identity. So if you have 11 protons, you are sodium, according to the periodic table. And if you don't have P table open, now's a great time to do it because we're going to use it again today. If you have 5 protons, you're boron, and so on and so forth. We can identify elements that way. And if they're atoms and they're electrically neutral, that is, they're not ions, then they must have the same number of electrons. But that leaves us some flexibility with neutrons, because neutrons don't have a charge. So I could have all sorts of different combinations of neutrons for a given set of protons and electrons. So if I do protons or electrons for each of these, I get 5. Because they're boron. They have to have 5 protons, and if it's neutral, I have to have 5 electrons too. You know, let's put the little charges here just so we know what those are. But the neutron, here, I have a mass number of 10 and an atomic number of 5. Remember, I subtract these to find the number of neutrons. So there are 5 neutrons here, but over here I have 6, and here I have 7. As far as chemistry is concerned, these are all the same. They're all boron. So if I do a reaction involving strictly boron-10 atoms and a reaction strictly with boron-12 atoms, I get the same product. So, like, if I reacted with, like, fluorine, for example, I would get BF3 or something. How do I know that? I've done this for years. How would you know that? You wouldn't. You would have to look it up. So, I'm just making up a reaction that's going on here. But the point is, they would all give you the same result, because they're all boron. Is there any noticeable difference? Can we discern a difference between these atoms using our senses? Like, can I look at it with some sort of tool? Or can I hold it and notice some sort of difference? And the answer is yeah, there is a difference. In fact, it's right here. It's this number, right? What is this number? Well, it's called the mass number, right? And the bigger that number is, the heavier the atom. So boron 12 weighs more than boron 10. And that checks out. It's got 2 more things in the nucleus, yeah? So they just weigh different amounts. And that has some consequences, none of which are particularly helpful for probably us in this class. But it is important to note that these isotopes exist. Isotopes have the same atomic number, or same Z, but have a different mass number, a different A. So if you're looking at species of atoms and they all have the same atomic number, they're all the same element, but they have different mass numbers, they have different number of neutrons, what you are looking at are isotopes. Now, can I add as many or as few neutrons as I want? It turns out the answer is no. The part about isotopes that is relevant to you, particularly if you are going into some sort of radiology, excuse me, is that some isotopes are radioactive and have particular medical applications. For instance, there are isotopes of fluorine that are used in positron emission topography. You give somebody a sample that they ingest. It is a sugar solution that has radioactive fluorine in it. And then it goes into their stomach or whatever, and it starts to decay. And the decay hits a detector and then tells you something about where that atom was when it decayed, because you can pinpoint it. But only certain isotopes of fluorine will do that. Particularly the ones with too few neutrons will do this. So knowing what isotopes are will be relevant when you get to radiotech and stuff like that. If that is your degree path, which I don't know because I can't actually see that information from just your name and your student ID on my class roster. So, but if you have any interest in that sort of thing, you can ask me in the Discord and I can find more information, because medical isotopes are something that are prevalent and fairly useful. Technetium is another one. If you look at technetium element number 43, depending on the periodic table you're looking at, it might be a different color or it might be a different font or something like that. Technetium is completely radioactive. It doesn't exist on Earth. There is none. You could dig everywhere in the entire planet and you'll find zero. And the reason for that is it's not stable. It has a half-life that's way too short. We had to make it. And so we're like, oh, okay, well, if I need something that doesn't persist biologically, I'll make technetium. And then I'll have somebody ingest it and see if we can, analyze where the electrons are coming out of, or gamma rays, or whatever. So that also has a medical application too. And I know a few of these, so I could actually, do more research and tell you about them later. I don't know why these didn't appear at the top there. But. All right, so there's our rubric. To identify something as an isotope, it has to have the same atomic number, but a different mass number. And like I said, not all possible combinations of neutrons are allowed. So the ones I showed you on the screen here, carbon-12, this is the most common one. Carbon-14 is very rare. So, if this were World of Warcraft or something, carbon-12 would be a gray item. You find it everywhere. And carbon-14 would be a purple. It's extremely uncommon. And that just has to do with relative stability or how they're made. For example, carbon-14 occurs from a radioactive process in the atmosphere. I believe? I want to say it comes from, electron capture of nitrogen or something like that. I had to look at a table of nucleides to do that. I don't know off the top of my head. But suffice it to say, it's made in very small quantities, and then is incorporated into things like plants, and then will slowly decay over the course of about 7,000 years or so. Let's see here. Other elements have more than 2 isotopes. So, for example, I think tin, element 50, has like 10 different isotopes. There are so many different isotopes, and they're all stable. Fluorine, on the other hand, only has 1. Sodium, I believe, only has 1. It's rare to only have 1 isotope. Usually you can have several. And then again, like we said, you can make whatever combination you want. Those isotopes are going to be called synthetic because we had to produce them ourselves. Now, later on in a future lab in, I want to say it's like experiment 5 or something like that, or 4. I don't remember the order for the online labs. I'm going to have you watch a series of videos on radioactivity from various isotopes. And you'll get to see what those particles do and how they behave under different conditions. Those conditions being like barriers being placed between them and the target, distance, and so on and so forth. Why do some elements have more isotopes than others? That's mostly just sort of a feature of how the protons and neutrons interact in the nucleus. You'll remember that I said that neutrons are like nuclear glue. If you have too many neutrons, what actually happens is the neutrons don't stick to anything anymore because they need to stick to protons. And neutrons themselves are inherently unstable. They need to have protons nearby so that they don't fall apart themselves, it turns out. If you have too few neutrons, then the protons repel and the nucleus falls apart. And you have to start doing stuff so that you don't have as much positive charge in the middle. So there's sort of a Goldilocks principle just right region. And depending on how many protons you have, there are different numbers of combinations that are valid. And then after a while, there's just no combination that appears to be stable. So once you go past element 92, which is uranium, uranium's the last stable element. Neptunium, plutonium, and americium, so on and so forth. Past 92, no combination of neutrons and protons will hold the nucleus together. There's just too much shit there. So I know that sort of doesn't really answer the question, and that's just what we observe is never a satisfying answer. But in this case, that's just what we observe. Now, something that we're going to do is we're not going to measure the mass of an atom like this. This is silly. Carbon atoms are extremely light. You could have 10 to the 23 of them before you reach even 1 gram. I don't want to deal with that. That's too tiny of a number. So what we're going to do is we're going to use instead this special unit called the atomic mass unit. And we have defined the atomic mass unit in a very special way that is so special we won't talk about it until chapter 6. It is a secret. But suffice it to say, for our purposes, the atomic mass unit is equal to a proton or a neutron. So if you count the number of protons or neutrons in the nucleus and sum them together, in other words, the mass number, you get the mass of that atom in atomic mass units, AMU. So carbon-12, which has a mass number of 12, would therefore weigh 12 AMU. And I can't get this to work. There we go. Now, what about an electron? Electrons are extremely tiny. In fact, they're so tiny that they essentially round down to 0. So we're just not going to worry about electrons. You would need about 1,800 electrons to attain a mass of 1 AMU. And it turns out no element has 1,800 electrons because the highest element that we go up to on the periodic table is 118. You need 10 of those smushed together before the electrons contributed meaningfully. And that's just not something that's going to happen unless you have a giant, giant molecule. Oh my goodness, the cat startled me. Hi. You startled me. I'm teaching. I sort of like leaned over and I heard meow. All right, so, oops, I'm not clicked on the right screen here. No, you cannot jump on my lap right now. This is a bad time. Now, it turns out that using this approximation only gives us answers that are approximately right, and that if we actually use devices to weigh things, we get close enough. And so for our purposes, this is going to be good enough. If I say carbon-12 weighs 12 AMU, and I say that boron-10 weighs 10 AMU, for this class, that's good enough. Down below, I have shown that you can use a device to weigh a boron-10 atom, and we get this conclusion. This is the relative mass of boron-10, and so this is the mass that we get as a result by doing a calculation. You'll notice that this rounds to 10, right? This is good enough. If you look on the periodic table, you'll notice that no numbers really land exactly on like 0, 0, 0, right? Oxygen's real damn close, 15.999. I can't think of any other examples off the top of my head that are that close. Fluorine right next door, 18.998. That's real close to 19, right? So some elements will land really close. And the reason for that is because their masses are calculated in this way. So this is what that number is at the bottom of the periodic table to some extent. On the next page, we're going to complete the story. But this is where that number is coming from. So when you look at the box that says boron, it says 10.811. And you'll notice that we got 10.013 for boron 10. That must mean that there must be a mixture, right? There must be boron 10s and boron 11s and boron 12s and so on and so forth. And there must be more boron 11 than boron 10 because the average is 10.811 on the periodic table. And so that's how we get these atomic masses. So atomic masses are just all the different possible isotopes that occur, averaged together based on how abundant they are. Now, there is a formula and a calculation you can do to determine average masses, and we're not going to do it because it's not important enough for this class. What I want you to know is that the periodic table number comes from the average of all the isotopes that are available. And if there are more of one isotope than another, that isotope contributes more to the average, and the average will be closer to it. For example, if I tell you that on on lab number 1, 80% of the class got 20 out of 25 right, and 20% of the class got 10 out of 25 right, you wouldn't say that the average was 15 because more people got a 20 than a 10, right? The average would be closer to 20. It'd be like 17 or something. It's the same thing with atomic masses. If there is more carbon 12 than carbon 13, so like let's say that like 99% of my carbon is carbon 12 and 1% is carbon 13, then the average would be somewhere in between. And in fact, because there's so much carbon 12, it would tilt way towards carbon 12, so it's very close to that. Likewise, if I go down here to this practice problem, let's suppose that bromine is half bromine 79 and half bromine 81. So if these are our possibilities, and it's half and half, what do you think the average mass would be? And you should be able to look at this and guess what the number is, and then check the periodic table and see if you're right, because this is actual data that I'm using. You can type that in the chat once you have an estimate of what the average mass should be based on this. No, this is not your permission to go on my lap, Krasnik. Very good, 80. And why'd you come up with 80? Well, it's halfway between 79 and 81, right? Because that's how averages work. And it turns out that that is close enough to get the right answer. If you look at the periodic table for bromine, and let's get the periodic table up on the screen here, because I can do that. P table. And then we will do, let's see, window capture. Oh, it already got P table. Perfect. So we'll do that. Look at that, it's right there. So if I go to bromine, I didn't actually click on it. There it is. I can see that the average mass, the atomic mass, which is this number right here on the bottom, really close to 80. Now, why is it off of 80? Why is it not exactly 80 if one way is 79 and the other way is 81? Well, it has to do with the reasons that we talked about before. The mass of each individual isotope isn't exactly 79 or 81. Turns out it's a little less. It's slightly less than the round number that we would expect. And again, that just has to do with, oh, I can weigh these actually very precisely. All right. So what I want you to do here is I want you to try and guess the atomic weight of this isotope. I have found a new atom X in like an alternate dimension or a parallel universe or something. I don't know. And so my atom is element 21, and 20% of the isotopes are X43, and 80% are X44. What would you predict the atomic mass would be on the periodic table? And then I want you to look at chlorine. Chlorine has two isotopes, and they're these, 35 and 36. Now, according to the periodic table, its atomic mass is 35.453. What must there be more of, 35 or 36? And what percentage of atoms weigh exactly 35.453? Now, I've put this down here. This is one of those, well, duh, this is the answer, and then you're going to say the answer and then trick yourself into thinking, well, wait, that's not the answer. Or you might just jump straight to the trick part. So be careful. I want you to type your answers in the chat. I'm going to give you like 2 or 3 minutes to do that. And then we'll go over the results together in just a bit. All right, one more minute. We'll go over the answers here. All right, let's go over the answers here. So I'm going to put this screen up first. Now, because these are one away from each other, you can pretty easily just say, oh, okay, well, it's mostly X44, so I would just say it's 80% of the way between the two. And you'd be right. So you could do something like this. Well, this weighs 43 AMU. And this weighs 44 AMU. So I'm going to be like this, so that there's 80% of this one and 20% of this one. So I'm 80% of the way across. If it was 100%, I would be over here, right? And if it was 0, I'd be over here. So the mass of the atom on average must be something like this. And that would totally work. And you could do that with any two endpoints. If you're just looking at two isotopes, you would just change what the endpoints are. Now, I could show you the math behind this if you're curious. You're not going to have to do this, but the mathematical way that you would do this is that you'd multiply the percentage times the mass of each isotope and then just sum those results together. And then I got to get my calculator to do that. I wasn't prepared to do math today, I guess. 0.2 times 43 is 8.6. And I'm just going to ignore sig figs because whatever. 0.8 times 44 is 35.2. And when you add these together, I don't know why I'm adding them together. I know what I'm going to get. It's this. And that's exactly what we predicted, right? So that's how you do it, is you multiply percent by the mass of the isotope, and you just sum all those together. You won't have to do that, but in case you were just curious. All right, so for the next one, let's do the same thing. Let's do what we just did. So I have chlorine 35, which weighs 35 AMU. And then I have 36 Cl. Turns out there isn't any 36 Cl. It's 37, but for the purposes of this example, you don't actually know that. And it still works out that I give you a true answer here. So, and we have right here, this is where our average is, 35.453 AMU. What is there more of, chlorine 35 or chlorine 36? Well, it's closer to this side, so there must be more of it, right? And it turns out that's true, because it's closer to weighing 35 on average. There must be more atoms of chlorine 35. Now, what percent of atoms have a mass of exactly 35.453? Well, I just told you. Here are the two isotopes. What do they weigh? 35 and 36. How many of them weigh 35.453? None of them do, is the correct answer. And this is where A lot of people get tricked. They go, well, duh, they don't weigh 35. They don't weigh 35.453. They weigh the other end, the bookends, right? And then you're like, well, wait a second, hold on. And then you confuse yourself, right? Isotope masses are not the same as atomic masses. So that number on the bottom of the periodic table box for your atom only represents the mass of an isotope if only one isotope exists for that element. One stable isotope, I should say. If there are multiple stable isotopes, you're going to have an average in some way, and then that number is rubbish in terms of what exists, other than telling you which one's most likely. So in general, if you round the average mass to the nearest whole number, that is the most abundant isotope. Just by definition of how this diagram works, right? Now, for two elements, that will be almost universally true. There are some exceptions. For example, bromine is kind of a nasty exception because there is no bromine 80. There's 79 and 81, but 80 doesn't exist for whatever reason. And then other atoms and isotopes have multiple different isotopes that are available, and so it's harder to do an average using a diagram when you have 3 or 4 different possibilities. So, as a general guiding rule, you can more or less rely on, round to the nearest whole number, that's the most abundant isotope, for the purposes of our class. But it will not universally be true. It will just most of the time be true. Alright, there's the homework practice for that section. So make sure you copy that down. I believe there's only one more thing to talk about in Unit 3, so let's... there's 2 more things. With periodic table and metals and nonmetals. Again, we're not going to do these 2 parts down here. Just because we don't want to waste time on electron configuration when it's not super interesting. But we do want to talk about the periodic table. So have P table open. And what I'm going to do is I'm going to start showing you some reactions of elements in water. Why is that a sound that we're making? Oh, okay. The cats are playing in a box, and I think one of them just jumped in the box and startled me. Alright, so we do want sound for this, and let's move this over here for me. Window capture 5, I want you to be... Oh, you can't find that anymore because I changed it. Okay, there you go. Boop. Alright. That's not the one I want to resize. I want to resize this one. Okay. Alright. We're going to put sodium in water. Now, on P table, if you have P table open, I want you to find sodium on the periodic table. And while you're doing that, let me turn this up a little bit. Watch this video that I'm showing you right here and make a mental note of what you see. So this is sodium metal put in water. That's kind of exciting. Let's watch that again. So we'll just let it fizz around. Oh, catching on fire. And then it explodes at the end. That's kind of weird. Is that the sodium that you eat? Yeah, it's the sodium you eat. However, the sodium that you eat is sodium ion, which is stable and safe. Sodium metal with the same number of protons and electrons is very reactive with water. It detonates. Alright. So that was sodium. Now what I want to do is I got to go to this person's page again. And I want to find potassium in water. Alright, and then we'll do this. Alright, so here's potassium. Again, look at the periodic table, find potassium. And here's what happens when I drop potassium in water. Now, looking at that, we'll watch it again here. There it goes. I'm going to just pause it on a frame so that you can see this. What differences do you see between the first one and this one? But what similarities are there? And you can note those in the chat. How is potassium similar to the sodium reaction? And how is it different? Now, while you're typing those into the chat, I'm going to go and get the next element, which is this one. All right, so this element is rubidium. And the symbol for rubidium is Rb. And you should try to find that on the periodic table too. And you might have started to notice a pattern by now. If you see the pattern of what elements I'm picking to show you, type it in the chat. All right, here is rubidium. It's so fast we have to do that in slow motion. So here it is in slow-mo. Looks like a miniature fireball or like Sonic the Hedgehog even just rolling about there. Like if I go to oops. If I do this. Oh, I hit explode, I guess. I unpaused the video. But you could see that rubidium doesn't last very long. And then it's done. They're all in the same row. Not the row is not the right word. Row is left to right. Oops, that's what I meant to do. Now I gotta do cesium. Let me get that off the screen real quick so I can find that. And this one is I have to do very quickly here. Right. So here's cesium. Yeah, column. There you go. So this is the last one on the column. This is cesium. And it's so fast, I'm going to hit play and it'll be done. So here you go. There you go. Wasn't that fun? Here it is in super slow motion. It lasts 2 frames. So a 30th of a second and it's done. And there it is, the 1 frame that we could catch it. All right, so we're starting to get a bunch of observations in the chat as people catch up, because I realize that I keep going, but people can pause the video and go back and do stuff. But all of these things are very important to note. Yeah, they both catch on fire. They all seem to be catching on fire. But as I go down the periodic table, the reactions are getting faster and faster and faster, right? Sodium was kind of slow. Potassium felt a little quicker. Rubidium was real fast. And cesium is like blink and you'll miss it. Now, I'm going to do one more element. And you might think it's francium, but it's not. I'm going to pick calcium. And I like this video because it actually shows you metallic calcium. This doesn't look anything like what you've probably imagined calcium to be. Your experiences with calcium are probably limited to things like milk, right? Where it's this white, precipitous entity. It's what gives milk its white color, right? It's what gives your bones their white color. But calcium is a metal. Calcium ion, when you take away 2 of its electrons, does create white solids. But calcium metal, like all other metals, is shiny and reflective. And we're going to drop it into water too and see what happens. Well, it's next to potassium, so it should do what potassium does, right? Ready? Nothing happens except this gentle fizzing. This is what calcium does in water. It just sort of like do-do-do-do-do-do-do. Now, it's fizzing pretty vigorously, but it certainly isn't catching on fire or exploding or anything like that. It's just making little farty noises, really. Okay. What conclusion do we draw from these experiments based on the position of the elements on the periodic table and what they did? And the conclusions that you drew, it seems like from the chat, was that all of the elements in that column tended to blow up. But then I gave you something that wasn't in that column, and what was the first thing it did? It didn't blow up. And it turns out that that is not a coincidence. Elements in the same column behave similarly. Wow, how did that manage to happen? That seems like a freak occurrence, but it turns out that the periodic table was designed by someone who had this idea in mind. So there's another example on there. The noble gases, helium, neon, argon, krypton, xenon, don't do anything. They're inert. Like all nobility, they sit on their asses and do nothing, right? We've stuck all of those elements in the last column of the periodic table. And I say we, but what I really mean is this guy. This is Dmitry Mendeleev. Dmitry Mendeleev, you can tell, is a very important scientist because, one, he has an awesome-looking beard, and two, they took a grayscale photograph of him, right? Those are how you know someone's important. They have a black and white photograph of them. I mean, somebody bothered to take it, or they were around when color photography hadn't been invented yet. In either case, they're important, right? Now, this scientist noticed the fact that certain elements reacted the same way with different phenomenon. For example, add to water. We're going to add all the elements to water. Only certain ones explode. For instance, if you add an aluminum can to water, it doesn't explode, right? Now, the aluminum is coated, but even if the aluminum wasn't coated with aluminum oxide, it would not detonate. That is good because we drink things that have water in them from cans. For example, deliciously refreshing polar seltzer. I'm almost out of it and I need to go buy more. If that were the case and water made everything explode, water would explode on contact with our aluminum cans, and then when you drank it, you'd be in for a real surprise. When you popped the lid open, instead it would be an explosion, and probably not great for marketing, right? So certain elements exploded on contact with water. Other elements reacted very violently with, say, like chlorine, or with metals, or so on and so forth. And what he did was he put all of those in columns. He said, okay, column 1, everything that reacts with water. Column 2, everything that fizzes in water. Column 3, reacts with some other thing. And what he was able to do, and I'll find his periodic table for you. He was able to line up... I don't know if this capture will work. Yeah, I can't find that window. There we go. So I want this over here. This is the periodic... Oops, I went off the screen for that. So this was the Mendeleev periodic table. And you can see that this is very different than what ours is because he has some elements that are sort of doubling over each other. Now, a fun factoid is that some of the elements that he that are on this periodic table right here, he didn't know about. For instance, all the ones in pink in the middle, actually, I think maybe all the ones in pink at all, were unknown. They had not been discovered at the time. And so I'm going to look at gallium, for example, GA. I don't know if you can see my cursor. I'm going to have to click on this window. There we go. Mendeleev did not know what this element was. It had never been reported, and he said, there's a gap in my periodic table. I bet there's an element out there that we just haven't found yet that has these properties. It's going to react similarly to aluminum and indium, It's going to have a density roughly between them. It's going to have these chemical compounds, formula properties or whatever. And it's going to make this reaction with chlorine. It's going to make this reaction with oxygen. Go and find it. And guess what? They later on found gallium, and it basically was exactly what he had predicted using this table. So the predictive properties of the periodic table are really, really good. And it's kind of because we have designed it that way. Now, there are over 110 elements. You'll notice that mine is incomplete because I haven't updated this picture. You do not need to memorize them all. That's ridiculous. Any instructor that makes you memorize the periodic table is basically making you do busy work. This is not something you should commit to memory. There is too many bits of information, and none of them are useful to your day-to-day life. Knowing that chlorine's atomic mass off the top of your head is 35.453 does not impress anybody. Trust me, I've tried. So don't do it. If you can list all the elements in order, nobody gives a shit. Trust me, I've tried. So just look it up whenever you need to. So keep p-table handy. Just type in ptable.com on Google if you need it, and then refer to it whenever you need to. Now, if you have p-table open, you're going to notice that there are a bunch of different colors for the various columns that are shown, and then over on the right, there's like a staircase sort of thing. And then down at the bottom, there's rows that are different colors too. The colors are important because they're identifying different groups that we have assigned and attributed properties to. A group is a series of elements that run up and down the periodic table. So, in other words, it's a column. Elements in the same column tend to react similarly. I know, I have 2 minutes. Give me 2 minutes, okay? No, you can't sit with me. Maya is here, and she wants to jump in my lap. I think I forgot to just give them more food, although I'm certain that I did. So I don't know. We're going to take a break in a second anyway, so I'll go check on them. So, groups are up and down the periodic table. Periods are rows that go left to right. The period is going to tell us some information that we need later, particularly for electron shells in Chapter 4, which we're going to talk about later today. There are other uses for this information for periods, but because the table is periodic, a period is each row, and every time you go to the next row, the properties that periodically appear happen again. For example, if I go from... Oh, I'm all zoomed in now. That's the wrong command. Hold on. There we go. For example, if I go to row 2 here... So here I have lithium, which should explode on contact with water. It does. It's very slow, though. And I go across and I go around to period 3. The property happens again, periodically. If I go to row 4, the property happens again, periodic. That's where the word periodic comes from. That's what it means. All right. I'm going to put this on the screen, but we're going to take our break now. When we get back, we're going to talk about what these groups are and what the important ones are to note. But until then, we'll take our 10-minute break. Let me get the timer on the screen here. And we'll get more music from Donkey Kong Country going. Oops, hold on. Right now. Warning, this next track may cause anxiety, nostalgia, goosebumps, and/or a sense of awe. Hi everybody, we're back. Alright, I have taken care of the issue with the cats, which was I forgot to give them food when I woke up today. So their bowl was mostly empty, but of course you know how cats are. They don't want to eat the last of the food in the bowl because that would, I don't know. It turns out I don't know how cats are. Other than they don't want to eat like the last like 10% of the food that's in there. Unless they have to. But they have been fed and they'll hopefully not be a bother anymore. So, alright. On the screen are different columns that are color-coded. And at the top you can see a bunch of names for the groups that those represent. Now, you're going to notice that hydrogen's in the middle. This is dumb. And I really don't know why they did this with this periodic table. So, just ignore this. It should be over here. This is not a thing that we will ever see. The first group that we're going to care about up here is the alkali metals. So, alkali metals are group 1. Or on this periodic table, they're labeled group 1A. And then next to those are the alkaline earth metals, which are group 2, or group 2A. Now, there are two numbering schemes for groups going across the table. The first is this A and B notation, where it goes A is only for the top stuff, and then B is down here in the middle. The other notation is that we just number everything going just across the periodic table. Like that. Now, the stuff down at the bottom, these don't have groups. So these numbers only are for the stuff above it. And I realize now that that was probably not a great place to put it, because these down here don't have any group to them. Even though they're lined up on my periodic table there, we don't consider them to have a group for a specific reason, which we'll get into in just a second. Going back to the group names here, chalcogens is dumb. Nobody needs to know that. Halogens, on the other hand, is common enough that you should know that. You've probably heard of a halogen lamp. Or halogenated, like plastics or something like that. I'm trying to think of things that might be halogenated that aren't just like chemicals, but I'm kind of coming up clueless here. And then finally, the noble gases are right here in group 8A. Now, what other features on this periodic table are worth knowing? the things that I want you to know are the following. So these groups right here, all the B groups, these are called the transition metals. And they are called that because they are the transition from the left side of the periodic table to the right side of the periodic table. Yes, that's the reason. It's real stupid. Down here, this first row, these are called lanthanoids. You might also see them called lanthanides. And the reason that they're called lanthanoids is because when you see lanthanum on the periodic table, you'll notice that the next number... I don't know why my pen did that. The next number is not 58. It jumps straight to 72. And the reason for that is because what you really do is you start here and then you go down to here. And you go all the way through the table and then you go back. And you continue. Same thing with the bottom part where we see actinium. These are called actinoids. Or sometimes you might hear them called actinides. And same deal, when you have actinium, you go from 89 down here to thorium, which I didn't draw very well. There we go. And you go across all the way to lawrencium, and you go back up, and then you continue the sequence. All right. The last thing that's important for us to know is this staircase right here. We're going to look at this staircase in just a little bit. So we'll do that in a moment. What I want you to do in the meantime, though, is I want you to look at these elements I've just sort of randomly selected. And in the chat, I want you to name them with their actual names. So you have to go to ptable and find them. I want you to tell me what period they're in, what group they're in, and then give me a category name that describes it. So I've listed some categories up there. You can use other categories to describe it from the previous slide that I've written down here. And if you don't find a category that satisfies your curiosity, I don't know. If you don't find a satisfactory category, just say none of the above. All right. I'm going to give you about 4 minutes to do that. I'm going to go figure out why there is a strange thumping in a cabinet. I suspect I know why because I'm looking at the cat who's doing it right now. And I'll be right back. 1 or 2 more minutes, and we'll go over the answers here. All right, let's go over the answers here. So this first one here is astatine. Oops, there we go. And it is in period... Oh, I gotta actually get the periodic table up here. So it is in period 6. And it is in group 17. You could also say 7A. And then I want to label it as one of these things. It is in the halogen category. There you go. We got K, which is a potassium. And it is in period 4. Group 1 or 1A. And it is an alkali metal. Then we got gold. Gold is in period 6. And it's in group 11, I think? Yeah, 11. Or 1B. And it is a transition metal. If you wrote none of the above, that's fine too. Then we have rhodium. Rhodium comes from the Latin, I believe it's the Latin word for rose. And you may have heard of it as rose gold. Rhodium is in period 5. Group. I don't know. Is it 9 or 10? 9, okay. And so that's 8B. And also transition metal. So you have them backwards. So period is up and down, and group. Oh, I'm sorry. Period is left to right. I'm reading what you're saying and not saying the right thing. So period is left to right, and then group is up and down. Let me go back to this page here. All right. So going across the table. So these are periods. And then going up and down are groups. So be real careful that you don't invert those. And those are mentioned right here. on this slide. All right, and then the last one, tellurium. Oop, different color, but that's okay. Tellurium is in period 5. Okay. Group. Trying to find it. There it is, 16. Or 6A. And there really isn't a good category for that. And so you should be able to see the period numbers and group numbers on p-table, if you have p-table open. In fact, if I just go over here and get it again. I think it's working again. Hello? Hello? Can everybody hear me? Okay, it says it's live again. I clicked on a thing and OBS crashed, which is... That's normal. Okay, everybody can hear me now. Okay, good. Yeah, I don't know what happened there. That was real bizarre. That has never happened before. Oops, I went to go turn on the image for the periodic table, and the whole thing just crashed. So I'll do this, and I'll hit this button, and you can see it this time instead of it crashing my program. There we go. So if I go like this, I'm just glad that I was able to restart the stream and it didn't make me make a new video. Because sometimes it does that if I take too long to fix it. Yeah, everything should be live again, so I apologize for that. So if you look at this, you could see here that here are my period numbers on the side. So, for example, tellurium would be in period 5 because it's in the 5th row. And it's in column 16, so it'd be group 16. So you can think of period and group as a sort of coordinate.